Hello everyone. Today, we're going to explore an important analytical technique used in chemistry called gas chromatography. Our group consists of 3 members, which is Izzah, Aisyah and Dinie. Firstly, gas chromatography is an analytical technique used for separating components of mixtures that contain gaseous and volatile compounds. The key to understanding GC is knowing that it works with 2 phases. First, we have the stationary phase, which remains fixed in place. Second, there's the mobile gas phase, which acts as a carrier to transport the sample through the system. These 2 phases work together to separate the different components in our sample. Here we can take a closer look at what a gas chromatography machine actually looks like. There are 2 main types of gas chromatography. First, we have gas-solid chromatography, or GSC. In this type, the stationary phase is a solid adsorbent material. The separation mechanism here works through an adsorption process, where components stick to the solid surface. However, the most commonly used technique is gas-liquid chromatography, or GLC. In GLC, the stationary phase consists of a thin layer of non-volatile liquid that is bound to a solid support. The separation mechanism in this case is a partition process, where components distribute themselves between the liquid stationary phase and the gas mobile phase. GLC is preferred in most applications because it provides better separation efficiency and is suitable for a wider range of compounds. Now, let's understand how separation actually happens in gas chromatography. When a sample mixture is injected into the GC system, each component in the mixture behaves differently based on its unique chemical properties. Components with greater affinity for the mobile phase prefer to stay in the carrier gas. Because they don't interact much with the stationary phase, they are carried down the column faster. As a result, these components exit the column earlier, giving them a shorter retention time. On the other hand, components with greater affinity for the stationary phase prefer to interact with the stationary phase coating. They spend more time being retained by the stationary phase. Consequently, they travel through the column slower and exit the column later, resulting in a longer retention time.
Next is components of GC. There are 5 main components: carrier gas, injector, column and column oven, and detector. The carrier gas is our mobile phase, helium, nitrogen, or hydrogen at 99.99% purity, flowing at 1 to 50 milliliters per minute. The injector vaporizes tiny samples, 0.1 to 1 microliter, at 50 to 400 degrees Celsius using split, splitless, or on-column methods. The column is 10 to 100 meters long, heated at 40 to 350 degrees Celsius, with polydimethylsiloxane stationary phase. Detectors like FID, TCD, ECD, or MS measure separated components with picogram sensitivity. Next is the working principle. Let's see how all these components work together. Carrier gas flows from the cylinder through regulators maintaining constant flow. Sample is injected through a septum and instantly vaporized in the heated port. Components separate based on their affinity for the stationary phase. High affinity means slower travel, low affinity means faster elution. Separated components exit sequentially and the detector generates signals proportional to their concentration. Signals are processed into a chromatogram showing peaks for each component plotted against time.
In this GC demonstration, the sample is injected and vaporized. The carrier gas moves it through the column for separation. Finally, the detector sends signals to generate a clear chromatogram on the monitor. Now, let's explore GC data analysis and learn how to interpret a professional chromatogram. Retention time is the journey duration through the column, used for identifying specific chemical compounds. Peak area and height measure concentration, providing essential data for quantitative chemical analysis. The baseline shows the steady carrier signal, while peak width reveals separation efficiency. Resolution measures the system's ability to clearly separate distinct chemical compounds into individual peaks. Integrated mass spectra provide unique chemical fingerprints, allowing definitive identification of unknown substances. Next, let's explore the diverse real-world applications of gas chromatography across various industries. GC identifies aroma profiles and verifies the purity of oils and alcoholic beverages. Forensics use GC to detect alcohol, drugs, or poisons in blood and urine. Environmental analysis detects pollutants like VOx in air, water, and contaminated soil samples. The petrochemical industry analyzes gas and gasoline composition for rigorous quality control. Pharmaceuticals utilize GC to test drug purity and identify harmful residual solvents in products. That's all from us. Thank you for watching.